Today we have the honor of hosting Professor Andrea Baldi from the Free University of Amsterdam. He did his master in chemistry in the University of Rome, La Sapienza, okay, and then he moved to the Free University of Amsterdam to perform his PhD in condensed matter physics. Then there he studied the properties of metal hydride thin films, okay, for hydrogen storage and smart window applications. And then in 2011, he won the Young Energy Scientist Fellowship from the Dutch Physics Institute, which funded the postdoctoral scholar at Stanford University. Okay, and there he started working on nanoparticles. Okay, by developing imaging and spectroscopy techniques to study this individual nanoparticle for applications in energy conversion and storage. From 2015, he went back to the Netherlands, okay, initially as a tenure-track senior scientist at the Dutch Institute for Fundamental Energy Research in Eindhoven, where he led a research group on nanomaterial for energy applications. In 2017, he won an NVO-VD grant from the Dutch Research Organization to study the plasmon activated catalysis. On 2020, he joined the physics and astronomy department at the Free University of Amsterdam as an associate professor, where he led a group focusing on plasmonic photochemistry. In June 2023, he was awarded an NVO grant to investigate selective plasmonic photoreduction of CO2 into added value products. Okay, and today, he's going to present a work which is titled Plasmonic Photothermal Chemistry, Nanoscale and Ultra-Fast Heating with Metal Nanoparticles. Professor Baldi, when you want.
Thank you very much, Christian, for your kind and long introduction. Essentially, a summary is I'm very old. That's thank you, Javier, Marta, and Christian for inviting me. As soon as I received the first email, I replied yes. I don't even know what was I being invited for, but I was really looking forward to it. And it's a pleasure to meet this very beautiful community of people working on nanotechnology and nanomaterials. So the title of my talk is a little bit of a mouthful. To summarize it, we shine light on nanoparticles and we heat them up. And we heat them up at, we create this temperature gradient that are very tiny in nanoscale and also very short in time scale if we do it properly. And I will show today how this heat confinement in space and time can be used to control and modify chemical reactions. And this is the Vrije Universiteit in Amsterdam, in case you've never been, on a this is considered a sunny day in Amsterdam, to be honest. We are sitting in this 1960s building, and it's full of asbestos, so it's going to be teared down, but now we get a brand new building over here. So if you come visit in a year time, we're going to be sitting in a brand new building. The research group looks a little bit like this. Of course, there is always people coming and people leaving. But if I were to kind of summarize the kind of research that we do, we are a collection of physicists and chemists that behave like physicists in disguise. So I'm actually a chemist by education, but I was hired by the physics department. I didn't tell them, and they made a mistake. So we still synthesize the nanomaterials. So we go in the chemistry lab and make our nanomaterials, and then we shine light on them. And the reason why we do it is because we want to activate chemical reactions. We want to look at the light that's scattered back and, for example, use it for sensing, either gas sensing or temperature sensing. We also make these nanomaterials in arrays and periodic arrays and try to exploit their emergent collective properties in order to maximize the response. But of course, I don't have time to go into everything that we do in the group. And so today I'm going to focus on really two results that are summarized by these two publications. And in a way, if you want to see an outline of my talk, if this is the title, Plasmonic Photothermal Chemistry, Nanoscale and Ultra-Fast Heating with Metal Nanoparticles, I will break it down in three parts. The first one is, what do we mean by plasmonic? And I hope this will not be too trivial. I think a Spanish professor once said that a third of every talk should be understandable by everybody. That's going to be this one. A second third should be understandable by most people, and the third should be understandable by nobody. So I hope I hope that I will carry you with me throughout the whole talk, but if you don't understand anything, you're probably in the last part of the talk. This should be understood by everyone. What do we mean by plasmonic? Also, why plasmonic photochemistry? And in the two examples that I'm going to be talking about today, really photothermal chemistry. So we shine light and we generate heat. And in the end, I will show you these two examples of how we can shine light on metal nanoparticle and generate heat both at the nanoscale and in very fast temporal scales. So in fact, I want to highlight the work that has been done for these two papers. The first one was really the work of a PhD student who graduated a couple of years ago, Dr. Rifat Kamaruddin. And the second one is really the work of a brilliant postdoc that now is a assistant professor in the section, Sven Askers. And he's developing this ultra-fast heating into a new research line. Okay, so what do we mean by plasmonic? And now, if you take a metal nanoparticle and you shine light on it, there can be a couple of things that happen. The nanoparticle can scatter light in all directions and it can absorb light. And the reason it does it is because metals are full of free electrons, and the electric field of the light can push these electrons back and forth and generate a resonance. And if you want to solve this problem from Maxwell's equation, it's a plane wave onto a spherical object, and it's rather complicated. So much so that if you read the book, the authors of the book that explains this me theory, they say the reader who has painstakingly followed the derivation acquired virtue through suffering. Now, we don't have time for any of the virtue or the suffering, so we're going to look at the approximation that works for very small particles. So in general, the way we conceptualize interaction of light with a particle is through the use of quantities that are called cross-sections. So we can define the scattering cross-section and the absorption cross-section, and the sum of the two will be the extinction cross-section. Now, these cross-sections have the units of an area. So in a way, the extinction cross-section, which is the sum of anything that this particle can do to light, for a microscopic object, that would be essentially the size of the area of the shadow that that object would cast on a screen behind it. So if you take a tennis ball, the extinction cross-section is pi times the radius of the tennis ball squared. And plasmonic nanoparticles can have scattering and absorption cross-section that are kind of weird, and I'll show you an example of it. But in general, we use this concept of cross-section to quantify their interaction with light. And you will see that scattering and absorption, they depend on a quantity that's called polarizability. And the polarizability of an object is a measure of how easy it is to polarize that object. So if you take, let's say, a metallic sphere in vacuum, you can define a polarizability of your object that is a metallic sphere in vacuum. And this polarizability will depend on the permittivity of the material, of the metal, and of the vacuum. So let's say that we take silver, because I'm going to use the example of silver. The polarizability of a silver sphere in vacuum will depend on the permittivity of silver and the permittivity of vacuum. And permittivity is a quantity that is intrinsic to a material. Polarizability is more of an object, right? So how can we find an expression for the polarizability without the virtue or suffering? We can do that if we consider particles that are much smaller than the wavelength of light. So if the ratio between these two dimensions is kind of inverted, if this is very small and the wavelength of light is very large, then the particle is essentially so tiny with respect to one oscillation of the electromagnetic field that we can consider it as an electric dipole. And so this is the so-called dipole approximation, where we can express now the polarizability of the particle as a typical polarizability of a dipole. And this is given by 3 times the volume of the particle times epsilon minus epsilon m over epsilon plus 2 epsilon m, where epsilon is the permittivity of the metal and epsilon m is the permittivity of the medium surrounding the metal. So if we say vacuum, the permittivity of vacuum, this would be 1, so this would be epsilon minus 1 over epsilon plus 2. Now what happens is that metals can have negative permittivity, and that's really a characteristic of metals. So there is frequencies or wavelengths of the electromagnetic radiation for which this permittivity of the metal can be -2 in vacuum, or -2 times the permittivity of the surrounding medium if you're not in vacuum. And this is the so-called Froelich condition. And who can tell me what happens at the Froelich condition? And I ask questions to the audience so I can drink coffee during the talks. What do you expect? Yes.
Alpha is infinite, no?
alpha diverges, right? It becomes very large. And what happens if alpha becomes, the polarizability of your object becomes very large? What happens with respect to how that object interacts with light? The cross-section of scattering and absorption also becomes very large. Of course, there is no single material where this can be perfectly happening. In fact, the permittivity is always a complex function, so you never have, perfect epsilon is -2. But you can imagine that if epsilon is in the vicinity of -2, the polarizability will diverge, and the scattering and the absorption cross-section will diverge, will become very large. And so your object interacts with light very strongly. It extinguishes a lot of light. Now let's take one metal, the typical plasmonic metal that we like a lot, which is silver. This is the silver permittivity. As I said, there is a real component and an imaginary component. For wavelengths between 300 and 500 nanometers, so let's say UV to the green, the imaginary component, which tells us something about the losses in the material, can be neglected. And so the permittivity of silver is just the real component. And then if you look at where that real component is -2, you will see that that happens around 350 nanometers. And now in the next slide, I'll plot the extinction cross-section spectrum for a silver nanoparticle, and it looks something like this. And so a silver nanoparticle in vacuum extinguishes light, scatters and absorbs a lot of light at 350 nanometers, huge peak. This is what we call a plasmon resonance. That's to answer this whole, torture that I imposed upon you, was to answer the question, what is a plasmon resonance? What do we mean by that? Now, this is a plasmon resonance. However, it is a plasmon resonance for a very small spherical particle of a good conductor in vacuum. And you actually have to put all these caveats in. If you remember, it's a very small, because we were in the dipole approximation where the radius is much smaller than the wavelength. Spherical particle, because this actually works if your particle is very tiny, so it's spherically symmetric. Of a good conductor, because we said the imaginary component of silver, we can neglect it, and in vacuum. But all these things actually affect the position of this resonance and the shape of this resonance. So in fact, the plasmon resonance will depend on the size, on the shape, on the composition, and on the environment of our nanoparticles, right? So for example, the plasmon resonance frequency depends on the particle size. You take a silver nanoparticle, in water in this case, you vary the diameter from 10 to 60 nanometers, and you will find that your plasmon resonance shifts from around 380 nanometers into the blue around 430. And it also increases because you have a bigger object, and the scattering and the absorption increase with the size of the particle. So larger particles typically have redshifted resonances and scatter and absorb more light. Now we can also tune these resonances by playing with the shape. So colloidal chemists, they have an infinite range of nanoparticles they can make. And so, for example, we can make gold nanorods in water with different aspect ratios. This is 88 by 23, 111 by 21, 128 by 17. So they're getting kind of skinnier and longer, and the aspect ratio is increasing. And so you see that the plasmon resonance shifts towards, let's say, from the red part of the spectrum or near infrared to the infrared part of the spectrum. We can play with that. Actually, there is a couple of resonances here because you also have two typical dimensions in a rod. You have the width and the length of the nanorods, so you can see both contributions here. But in general, particles with a higher aspect ratio also have redshifted resonances. Now, plasmon resonance frequency depends also on the particle composition. So if we take silver versus gold, this is 40 nanometer silver nanoparticle in water, and they have an extinction cross-section with a peak around 400 nanometers, and gold has a smaller extinction cross-section with a peak around 530. And actually, silver looks yellow. So why is a suspension of silver nanoparticle in water yellow? Does anybody know? Raise your hand. Sip of coffee.
Does it absorb the complementary wavelength?
Yes, it extinguishes everything that is in the blue and maybe UV part. And if you've been in a clean room where they do like photosensitive polymers, you know that they filter out all the UV light and the blue light to avoid their polymer to develop, and the lights are yellow. And if you have a very sensitive polymer, then you also cut off all the green and your light will be red. No. I had enough time. That's perfect. Thank you. Another thing that is really impressive of this plasmonic nanoparticle is that here I'm plotting for a 40 nanometer diameter particle, pi r squared. And it's this dashed line over here. So this is the geometric cross-section, and this is the extinction cross-section. What this says is that at 400 nanometer, a silver nanoparticle in water of 40 nanometer in diameter, it casts a shadow, an ideal shadow in a screen behind it that is several times its size. And so some people depict it using Poynting vector line. Essentially, plasmonic nanoparticles can have extinction cross-section larger than their physical size. The way I tell it to my students is plasmonic nanoparticles can cast large shadows. They have giant egos. And if you tune it properly, they can cast a lot of big shadow behind them. Now, the final thing is that plasma resonance can also be tuned by the environment. So you take a silver nanoparticle, I think this is also probably 10 nanometer, and you vary the refractive index from 1 to 1.5, let's say from vacuum to surrounded by glass. There's a huge shift in the plasma resonance, which can be used to detect, for example, small changes in the refractive index where you have a delta lambda over delta n that is larger than 100 nanometers per unit of refractive index. So this can be used, for example, for glucose monitor, where if you have more glucose in water, you have a slight change of refractive index. And then if you have a very sharp plasma resonance, you can detect that. So essentially, plasma resonances allow us to play with the light-matter interaction at the nanoscale, and also we can decide which color we want them, because we can tune these resonances essentially wherever we want. Okay, and then the second question is, why do we want to use it for chemistry, and how can we use it for chemistry? And I will show you one slide on, in general, how we can use plasmonic for photochemistry, and then I will show you what kind of physics we need to think about when we think about photothermal chemistry. How much heat do we generate, and how do we conceptualize that? Now, there are a couple of reasons why we want to use this for chemistry. We want to use light interaction on metal nanoparticles for chemistry. The first one is that metal nanoparticles, we have seen it before, they can focus light on the surface. They have large shadows, they cast large shadows. They essentially focus electromagnetic radiation at the surface. What I'm plotting here is the usual silver nanoparticle 10 nanometer in vacuum, and the blue shaded areas are the electric field E squared enhancement. So E squared divided by E0 squared, where E0 is the electric amplitude of the incoming light. So I'm plotting the intensity enhancement at the surface of this nanoparticle, and you see that the electromagnetic field intensity is enhanced by 450 times in a region that is probably 1 or 2 nanometers on the surface of a metal nanoparticle. And if you remember, this nanoparticle scatters and absorbs light with a wavelength of 350 nanometer, which to scale to this nanoparticle, it will look something like that. So this tiny object can take electromagnetic radiation that has a typical period that is very long and kind of compress its energy into a surface into a region that is deeply sub-wavelength. How can we use it for chemistry? Well, you can think that any photocatalytic reaction will start by excitation of an electronic system to a higher electronics level, for example, and it will always be modulated by the intensity of the electric field through the Fermi-Golden rule. So if we now have an intensity enhancement of orders of magnitude, then the rate of photocatalytic reaction can be enhanced dramatically, precisely at the surface where you have also catalytic properties because of the catalytic properties of metal nanoparticles. Of course, this is also the basis for a lot of the surface-enhanced Raman scattering techniques that is proportional to e to the power 4. So if you have a plasmonic enhancement, you can even do single molecule vibrational spectroscopy with SIRS. We use it in our lab also to do gas detection, because anything that happens in the high intensity field, plasmonic field, will be very visible optically. This is the first reason. The second reason is not related to what happens outside the nanoparticle, is more related to what happens inside. So what happens when we absorb a photon in a metal nanoparticle? It kind of looks similar to what happens when you absorb a photon in a semiconductor, where you have a photon coming in and an electron from a valence band being excited to a conduction band and leaving a hole behind. Now, in a metal, something similar can happen where a photon is absorbed, you leave a hole in the, let's say, in the sea of Fermi level electrons, and then you excite the electron into an empty state. However, a metal doesn't have a band gap, so there is a continuum of energy level, which means this excitation will thermalize extremely quickly. And so the timescales of this excitation is typically between 1 and 100 femtoseconds. Now, how do they thermalize? By scattering off each other, electrons with electrons, electrons with photons, electrons with defects, electrons with surfaces. And this kind of relaxation happens in the order of picoseconds. And eventually, it will lead to electron-phonon coupling. So the nanoparticle, the lattice of the nanoparticle will start to heat up. And then eventually, the nanoparticle that is hot will start to heat up the environment around it in the order of hundreds of picoseconds up to tens of nanoseconds. And so now we have taken energy of a photon and we are creating heat locally. And of course, we can think of ways in which we can apply this phenomena for catalysis and for chemistry. If you are fast enough, you can harvest these electrons and holes and do, for example, reduction reactions and oxidation reactions. And we have done quite a lot of work on, for example, synthesis of nanomaterials driven by hot charge carriers. But if you're not fast enough, still you're heating up the nanoparticle, and any chemical reaction goes exponentially faster at higher temperatures. And so you can heat up locally and activate chemistry locally. And that's actually what I want to show you a couple of results on, really about this photothermal effect. So translating photon energy into heat and controlling that heat both at the nanoscale and ultra-fast timescales. Now, before we go there, I need to set kind of the physics of how this process happens. And so the first example will be under CW excitation. So we're going to shine a laser onto a single nanoparticle, and we're going to heat up the nanoparticle, and we want to do something at the surface of it. But then the question is, how hot can we make it, and how do we conceptualize it? So the first physics background is really about the photothermal heating of a nanoparticle under CW illumination. Okay, if we think about it, let's say we have a piece of glass, and we have a nanoparticle sitting on top, and now we shine a laser onto it. There are two things that happen. The nanoparticle will absorb light and will heat up. And the rate of heating will be given by the absorption cross-section, that if you remember is an area, times the power density, which is watts per unit area. So the multiplication of the two is simply watts or joules per second. That's how much heat we are creating in a nanoparticle for any given second, right? And it's called the heat generation rate. Now, at the same time, the nanoparticle is getting hotter and hotter, and as it's getting hotter, it's dissipating heat into the environment. And this cooling rate also needs to be taken into account. And the cooling rate, or heat dissipation rate, it's depending on the thermal conductivity of the environment, the particle surface area in meters, and the temperature gradient across the surface. Now, this, if you think about it, this makes sense. The thermal conductivity of the environment, if it's very good, the heat dissipation will be very fast. Also, if the particle has a large surface, there is more opportunity for the heat to get out of the particle into the environment. And as the particle gets hotter, the temperature gradient becomes larger, and then the heat dissipation also becomes faster. In general, in physics, if you have a gradient of an intensive quantity, you have a flow of an extensive quantity. And so if you have a large gradient in temperature, you're going to have a strong gradient, a strong flow in heat. Now, we want to find a solution for a steady state condition. So what is given a certain irradiation intensity, what is the delta T of the particle? So how hot can we make it with respect to the environment far away from it? And so essentially, we need to equate these two, heating generation rate and heat dissipation rate. And if we equate the two, and you do a little bit of mathematics and an integration using the right boundary conditions, in fact, from a physical mathematical perspective, is the same problem of the electrostatic potential of a charged sphere. So something that we all did in electromagnetics, I think. And so if you take a spherical particle with a certain radius r, in a medium of thermal conductivity kappa, the steady state temperature increase, or delta T, which is the temperature outside of the particle, so at a distance from the center r, where r is equal or larger than the radius. So we are, let's say, plotting the temperature outside of the particle, minus the temperature of the ambient, that's the delta T. So it's a temperature increase with respect to the ambient, is given by the heat generation rate divided by 4 pi kappa r. And this is exactly the same equation that you see in the charged sphere, right? So how does it look like? It looks like this. So the nanoparticle is under CW heating, and the temperature gradient decays as 1/r as you get out of the particle. And in fact, the temperature inside the particle is rather constant. The reason for it is because the thermal conductivity of metals is typically orders of magnitude far higher than the thermal conductivity of anything outside of a metal, and so the temperature equilibrates quickly inside. And then this is interesting for us because this means that at the surface of the nanoparticle, the temperature is going to be high, reactive chemical reactions are going to be very fast, and as soon as you're a few nanometers away, the chemistry will stop. And so the first example that I'm going to show you is precisely exploiting this temperature gradient in activating chemistry locally at the nanoscale. The second example, however, has to do not with CW illumination, but with pulse illumination. And in pulse illumination, you have a pulse of light, and then after a certain amount of time, which is determined by the repetition rate of your laser, then you have another pulse of light. Now, in this case, we cannot define a steady state temperature. We cannot say the nanoparticle is always a certain delta T hotter than the environment, because as soon as the pulse arrives, it heats up and then it cools down of the order of nanoseconds. That's the cooling rate. And then maybe another pulse is coming, the temperature goes up and then it cools down, and then another pulse is coming and so forth. But one thing that we can determine is how hot can we make it? Like, what is the temperature at the maximum transient temperature increase? And now, again, is depending on the absorption cross-section and the irradiation, but there is other parameters that enter, in particular, the repetition rate, the mass of the particle, and the specific heat capacity. Now, if you plot this temperature profile, we did these calculations for a gold nanoparticle on silicon dioxide. This is a gold nanoparticle, 100 nanometer, and there is a little piece of glass. The nanoparticle is sitting a little bit inside the silicon dioxide, and there is air around it. And then we shine with a laser pulse that is tuned to the plasmon resonance, and we vary the pulse length. Now, this is all calculations. So I say we shine a laser pulse, but it's just COMSOL, okay? And then we vary the pulse length from 50 femtosecond to 5 nanoseconds. And what you see is that the maximum temperature that this particle experiences when the pulse arriving, it really doesn't depend at all on the pulse length, unless you have very, very slow pulses. Like at 5 nanoseconds, okay, the heating is so slow that it overlaps with the cooling that is of the order of nanoseconds. But for the rest, we can always get this nanoparticle to the maximum temperature because the cooling is so slow that any pulse laser source more or less will give us the maximum temperature. Okay, this is how we conceptualize how hot we can make nanoparticles in the lab under CW and pulse. Let me show you how we use them for chemistry. And the first example is really on how we confine heating at the nanoscale. And the chemical reaction I'm going to talk about is nanomaterial synthesis. In particular, what we wanted to show is that we can control the synthesis of other materials at the surface of a single nanoparticle. And we were not the first one. Many people had tried to use light to grow materials controllably at the surface of plasmonic nanoparticles. However, it's kind of complicated. So typically you get larger structure, is not very well controlled. There is probably some particles inside these large crystals. There is definitely particles here suspended on a substrate, and they were growing indium hydroxide microcrystals. Here there is a little gold nanoparticle, not so little, and this is a germanium that is growing on top of it. Some of the problems were typically these structures were very large. There was not fine-tuning of the nanomaterial synthesis at the surface. It was unclear whether this was a purely photothermal or an electronic process. And so we wanted to try to develop a strategy to be more controlled and actually study this process in real time. And so our approach was to use microscopy to activate the photothermal growth of a core shell nanoparticle. So the way we did it, we put gold nanoparticle on a cover slip, and then we put it into a microscope that allows us to do dark field scattering microscopy and spectroscopy. What this means is that we have white light, which is reflected in a dark field reflector. This is a white beam of light, and it's transformed into a hollow cylinder of light. So we only send light on the outer sides of the objective, and then we focus it onto a single nanoparticle. And our objective is built in such a way that it can send light at a very high angle, but it can only collect light at a lower angle. So if you don't have anything, let's say you have a perfectly flat and clean microscope slide. In an ideal world, that never happens, but let's assume that you can get there. Then the light that is coming from the objective is reflected back and is never picked up by the lower NA of collection. And so what you see is completely black. Now, as soon as you have a little bit of a speckle of dust on your glass slide that scatters light in all directions, that's when you see it. And now if we put gold nanoparticle, they scatter green light very efficiently. And so we can collect the green light be scattered by the gold nanoparticle, and we collect the plasmon resonance. And then we can collect the plasmon resonance of individual nanoparticles. But we can do more because we can switch from white light to a laser in the same setup. And now instead of doing this dark field reflection and hollow cone of light, we just put a 50% mirror. We bring all the laser power onto the same particle that we took the plasmon resonance of. And we irradiate it when this nanoparticle is in a flow cell, and so we can put reactants into it. So we heat that very same nanoparticle for a certain amount of time. In this paper, we're doing 15 minutes irradiation, and then we switch back and look at the plasmon resonance again. And when the kind of reaction that we wanted to activate is a Syria growth reaction. So it's cerium nitrate, and if you heat up at 90 degrees C for 5 hours, you can generate a shell. So we know that this reaction is temperature activated. So we did it on many single nanoparticles, and a typical experiment looks like this. You have a gold nanoparticle at the beginning that in dark field, everything is dark except that little speckle of dust that is your gold nanoparticle that scatters a lot of the green light, and so it looks green in your alignment camera. And if you measure the plasmon resonance, it will have a peak, a scattering peak at 554 nanometer that's in the green. Then you shine a laser for 50 minutes, and you look at the nanoparticle again, and it has turned into a red dot. And if you measure the plasmon resonance again, it's now at 626, and it's much stronger. And we did these experiments also on a TEM grid so that we could look at the nanoparticle after laser irradiation. And indeed, we can see that there is a Syria shell grown around it from EDX data. Now, this was really beautiful. We could grow controllably a Syria shell around the nanoparticle. But the first question that we asked was, how does it grow? Like, does it grow linearly during the 15 minutes irradiation? Does it grow all of a sudden? Does it grow all at the beginning? And so forth. And we didn't have a lot of way to measure it, but we were shining a laser. And so we thought, well, we're shining a laser during this 15 minutes irradiation. We are heating up the nanoparticle. Why don't we collect the inelastic light scattered back? So why don't we look at the photoluminescence or any other signal that is coming out that is inelastically scattered? We cannot collect the green laser, otherwise we fry our detector, but we're going to filter the green radiation and look at, filter this 532 nanometer and look at anything that is being reflected back. And if you do that during the 15 minutes laser irradiation, you do see a trend, but you don't really understand anything of what's going on. And the reason for it is because this inelastic light scattering contains signal from the photoluminescence of the gold, any photoluminescence from the quartz substrate, any Raman scattering that can be in the solution. And so what my PhD student suggested, it was like, well, why don't we subtract the initial spectrum from all the other ones so that the standard background contribution can be canceled out. And when you do that, you get a trend like this. And in fact, what turns out is that the photoluminescence of plasmonic nanoparticles, it scales with the scattering cross-section. Now, if you remember, when you take a nanoparticle and you make it bigger, the plasmon resonance shifts towards the red. And so the scattering is shifting towards the red. And so if you do the delta PL, it should look like a delta plasmon, delta scattering. And that's exactly what we see. This is a positive plasmon resonance minus a negative plasmon resonance. So from the shift in the peak position, we can also tell you how fast is the nanoparticle growing a shell around it. So that's what we plot. We plot the Syria shell thickness as a function of time, and we saw that it was actually pretty fast at the beginning and then slowing down towards the end of the 15 minutes irradiation period. And we think that the reason for it is because the nanoparticle is heating up under the 532 nanometer irradiation, but as you grow a shell around it, the plasmon resonance is redshifting, but the laser irradiation is staying there, and so it's cooling down. It doesn't heat up anymore. So it's kind of a self-limited process. The other question that we wanted to ask is, okay, we demonstrated for Syria, but can we grow anything? I mean, is this really purely thermally activated? And in principle, we could. And so we said, okay, let's try to substitute the cation with another cation, zinc, and maybe also the anion for sulfur, to demonstrate that we can, in principle, grow any stuff that we want. And so we did a lot of experiments. I'm just going to show you visually one experiment that I thought was the coolest. This is a dark field image of many gold nanoparticles on a dark background, of course. And these are all individual gold nanoparticles. And then what Rifa did, he flew the Syria growth solution and focused the laser onto this one, then washed everything away with water, and then flew the zinc oxide solution and focused. Oh, someone is taking control. And flew the zinc oxide solution on this one, and then repeated the same for zinc sulfide. And at the end, the sample looked like this. So we could grow different semiconductors on the same sample on adjacent nanoparticle. And what I find really beautiful is that, for example, this gold nanoparticle that is sitting maybe 5 microns away from it is completely untouched. Like we're really localizing chemistry on the surface of an individual nanoparticle. Now, the last example, the second example that I wanted to give you, this is going to be a little faster. I have no idea how I'm doing with time. I hope you don't hate me. No, I'm good. Okay. It's about confining heat, not in space, but now in time. And the way we do it is with this pulsed laser excitation. This is not experimental work, I should mention. This is all done in COMSOL, but Sven, who's this postdoc that did this COMSOL work in my group before, now he has his own research group, and he's expanding this with an experimental setup. So we already have a experimental setup working to test pulsed heating for heterogeneous catalysis. Now, why do we want to do it? What is the motivation behind this? Now, if you are running a heterogeneous catalytic reaction, you're always running a trade-off. And the reason for it is because typically we run catalysis in a steady state. So we have a catalytic reactor and we apply a temperature. And that temperature is the temperature at which we run our reaction. But this imposes some thermodynamic limitations. Now, why that is the case, I can show you with one example. Let's consider a simple reaction. A plus B gives AB. And let's say that this is a heterogeneous catalytic reaction. So you have a catalyst that is here represented as a black bar. You have A and B, and they can adsorb on the catalyst. And when they're both on the catalyst, they can find each other. And if they overcome an activation barrier, maybe they can form the product AB. And then there will be also some barrier towards the AB desorbing from the catalyst. We can also describe how densely populated is the catalyst surface. And the way we do it is with the concept of fraction of catalytic sites. So theta A would be the fraction of catalytic sites that are occupied by the element A. Theta B is the same for B, and theta star would be the fraction of catalytic sites that are empty. There is no A or B on it. Now, what happens at different temperatures? Here I'm plotting the coverage fraction theta A, theta B, and theta star as a function of temperature, or if you are in CW, so continuous wave irradiation as a function of laser intensity. Essentially, how hot are we making the catalyst? Now, if A and B have similar adsorption property on the catalyst, essentially at room temperature or at cold temperature, the catalyst will be populated by A and B 50-50. So the whole surface is covered. And the percentage or the fraction of free sites will be 0. And the problem is that if you are at room temperature, there is essentially no energy to overcome this activation energy barrier. And then what you do is, okay, now I'm going to heat up my catalyst in order to give it enough energy to form the products. But if you heat up the catalyst, then the surface coverage of A and B will go down and the fraction of empty sites will go up. And so now you have enough energy for A and B to react with each other and form the product, but there is no A or B on the catalyst. And so if you plot the amount of products that you form per second, which is called the turnover frequency, then you will see that there is typically an optimum at an intermediate situation where you have a sufficient turnover frequency. And this, of course, corresponds to a state where the catalyst is essentially mostly empty. So this is the kind of compromise that you always have to play. You want to heat up the catalyst enough to give it catalytic activity to make the products, but as you heat it up, you're essentially emptying the catalyst from reactants. And so you're limited in the amount of products that you can form. And now the question is, what if we heat up the catalyst not continuously? What if we have a catalyst that is always cold? And all the A and B are sitting on a catalyst, and then all of a sudden we come with a pulse of light and we heat up the catalyst very quickly of the order of picoseconds and react everything that is on the surface. And then after this, the next pulse is coming. Before the next pulse is coming, the catalyst has cooled down again in nanoseconds, and the catalyst and the A and B are sitting again, and then we come with another pulse. Can we do better than the steady state catalysis? So this is the kind of calculations that we did, and in fact, we can. So what I'm plotting here is the turnover frequency is exactly the same plot that you see here. So for A and B, here you see that the turnover frequency under steady state illumination or steady state temperature has a maximum. And you see the same here. So this would be continuous wave or steady state. And the turnover frequency is very low at very low intensity, and then will be maximized here, and then it goes a maximum over here, and then it goes down again. So this is the turnover frequency as a function of intensity. But now, if we have a laser pulse, we can also vary the repetition rate, kind of the sound of our laser pulse, the music that we're playing. And if you vary the repetition rate, there is certain regions of intensity and repetition rate where the turnover frequency is orders of magnitude larger for the same intensity. Now, what is happening here? We can have a look at it. Now, I know that this is a lot, but I will guide you through it. So this is the temperature of the catalyst for one pulse. The catalyst is cold until the pulse arrives. The temperature shoots up very, very much. And then on the order of nanoseconds, it will cool down again. And then the next pulse is coming, and the temperature goes up, and then it cools down of the order of nanoseconds, and so forth. If you look at the surface coverage, the catalyst is essentially almost fully coated with A and B. This is not exactly at 0.5, and there are a few empty sites because we are running this reaction at 363. That's not room temperature. But we have a lot of A and B on the surface, and then the pulse is coming, the catalyst is getting super hot. Everything is empty, so the fraction of surface sites becomes essentially 1. We empty the catalyst right away, but we have sufficient time during this heating to form a lot of product. So this is the amount of overall product that we form in the pulse regime over one pulse, and this is the amount of product that we form in the CW regime. So the difference is striking, and so we can form a much, much higher amount of product if we pulse it, and if we tune it properly. And of course, this tuning is crucial, so you have to work pretty hard, pretty close to the photoablation limit. You will see that the advantage with respect to the CW is typically on the right side of these plots. And here, this region is where essentially we photoablate our catalyst. So we need to be pushing the catalyst quite hard. We have to be sensitive to collective heating effects. So we don't want the heating to be spread out from one particle to the next. Otherwise, we heat up everything in a steady state. We go back to the steady state, and we don't gain anything from this. We think that there is a lot to gain in playing the right music, playing the right tune of our laser. Because catalytic reactions, they have a certain rate of adsorption and desorption and product formation. And if we can play with the repetition rate of a laser in order to play the right sound, we think that we can really maximize that kind of efficiency, conversion efficiency. And of course, since you're working close to the photoablation limit, you have to mind the material stability. And so we are also exploring plasmonic materials that are refractory, like titanium nitride, hafnium nitride, zirconium nitride. These have plasmonic properties, but they're still refractory, so they can withstand thousands of degrees. But there was a paper a few years ago called Applying Plasmonics to a Sustainable Future that said in the introduction, Plasmonics offers the ultimate spatial and temporal control over light and photochemistry. And I cannot think of a better sentence to summarize this talk. Thank you.